Hello everybody and welcome to another live coding episode of the Raspberry Pi Pico emulator. So I see we already have Nekati. Hi Nekati, good to see you here again. Today, and hi Steve, great to see you as well. Let me share my screen. And today we are going to start with last time we did the timer alarms, and we had some place where we weren't sure whether the interrupt force wins over interrupts enable. Apparently Graham from the Pi, I think he works on the Pi or something like that. I have seen him before, and he commented about something like running those tests from the SDK repo would be cool. So I asked him whether he knows which one is the correct one, and he says interrupt force wins over interrupt enable. So we will fix that in a moment. And hi Valeria, good to see you. And this week Valeria was also really active, just like the week before, and he did really some really interesting and meaningful contributions. It all started when he opened an issue about the hello timer, one of the examples from the Pico examples repo that produces invalid output. If you take a look, it says hello timer v fired. And you probably can you can probably see that what is timer v? It's probably 0 or 1, but anyway, you can see that repeat at v. So basically it seems like printf had an issue printing numbers, because if you run it on a real Pico, you see that it says timer 1 fires and repeat at etc. So I figured out it might be because we haven't implemented the integer divider. So we checked like the reads and writes, and we found that it indeed reads and writes from the SIO addresses where the integer divider is implemented. And then Valeria actually went ahead and implemented this divider, so we will take a look at that in a second. Let's actually go to the commit history. So as you can see, this is our commit last week, and then we had those two commits from Valeria. So not only he did the integer divider, he also did spinlocks, and he also added the reset-based peripheral, which is super simple. Let me show you. This is here. No, reset reset. Yeah, it's just 3 registers with some very simple logic. And the reason he did it is just to reduce the amount of unimplemented peripheral read-write warnings that we get. So now if I just, npm start, I mean, you won't see them because we implemented that, but I only got 1.5 screens of those warnings. The good news is that we are going to implement these pads, so we will see less warning in a few. Hopefully after this session we won't see all those pads and IO warnings, so it will be cut by half. And he also implemented spinlocks. So for those of you who aren't familiar with that, I mean, I guess most of you haven't spent time reading the datasheet like I did. So the integer divider is just like an additional instruction or way to divide 2 numbers. That's because the ARMv6m doesn't include a divide instruction. So usually, I guess the compiler implement that in code, but they wanted the Pi Pico team wanted us to have more efficient way to divide numbers, so they have implemented it as a peripheral or as part of the SIO port they implemented this functionality. So it's not part of the microcontroller core, because that's what ARM does, create the specs for the core and the instruction set. Rather, they implemented it as a peripheral. So we'll take a real quick look at what Valerio did there. I think he did an outstanding job, because he also, let's go to SIO, he also sort of compared it with the silicon, with the physical hardware, and he implemented a bunch of stuff that wasn't even mentioned in the datasheet, such as dividing by 0. That wasn't really explained by in the datasheet, so he just experimented and found out how that works. So basically, there are like a few registers, unsigned dividend and signed dividend, and unsigned divisor and signed divisor, and writing to those registers actually starts the division operation. Either if you write to the unsigned ones, it's unsigned division. If you write to the signed ones, it's signed divisions. And then you get the results in the quotient and remainder register. So basically, there are like 1, 2, 3, 4, 5, 6 registers, and there is also like this CSR, which is just the status registers that tells you whether the result is ready. So these are like all the registers of the divider, and it doesn't seem to be a lot of code. Like, it's just we can take a look at the diff, but basically just those registers for the state, and this is like the code that actually performs the division and calculates the result and the remainder. This is like the division by 0. But I think what really took a long time is to come up with the tests. And as you can see, there are like all those tests. So starting from line 39 until 140, 100 lines of tests. And they check signed division, unsigned division, dividing by 0, etc. I actually see one of the spinlock tests slipped into here. So let's just move it out of the divider. And there is also a warning here. Yeah, I guess Valerio forgot to uncomment this. So basically allowing this test to run against the hardware by setting an environment variable. So let's just commit this small fix. Test SIO allow running tests against hardware set, and let's actually do it. The test GDB server to the environment variable to the address of the OpenOCD GDB server, maybe of the Pi Pico OpenOCD GDB server. Cool. We did that. Yeah, and as for the spinlock, it's pretty simple. It's just I think one variable that has the status of all the spinlocks, and then there is like somewhere, yeah, there is like if you write to it, then it just I think clears that bit, so it releases the lock. And if you read from it, it checks if this lock is already locked, then it returns 0. Otherwise, it acquires that lock, that specific bit in the spin lock, and returns the value of the. Should it return? I guess it should. Maybe that's. Let's take a look at the datasheet for a moment. Spin lock. What does it return? Not here. Spin lock. And we will probably have to revisit this this code, the divisor, the integer divider, and the spinlocks when we go to multicore, because as Graham mentioned, the divider is like there are two of them, one per core. The spinlock, of course, it's shared between the cores. So well, let's see. Read value is non-zero if the lock was successfully. Okay. Non-zero. Okay, I think at least yeah. Okay, yeah, that's true. That's correct. You did your job well, Valerio. It's the actually I think you also verify this against the hardware, so that's the best form of verification. So yeah, so let's just run those yeah. Let's run those tests one more time against the hardware. So I have my OpenOCD running here, and let's just get the IP address of this. That's interesting. It just stopped responding in the middle of the how do I kill this SSH session? Yeah. Let's try through SSH again and hope for the best. Yeah. So this is the IP address, so we can set it. That was yeah, it's the spec file. Where is the SIO spec? We should probably move this code at some point into some test utils, because it's already repeated in 2 tests. So there is no reason to repeat this code. Anyway, so let's set this and then npm test, and we want to run them one by one, and only the SIO test. And we need to restart OpenOCD. And now it's waiting for connections, and let's see if it's actually connecting to the OpenOCD. Yeah, you can see like all the connections, and you can see that all the tests passed. So that's really cool to have this like ability to test against the silicon. Let's remove this, and you can see like each test take like 200 milliseconds, but if we just run the same locally, each test take like a few milliseconds. Just a small number, so it's a big difference running locally or like against the simulator or the RP2040. Anyway, so that was a quick review, 10-minute review of what happened this week. Before we move on to doing the GPIO, to continuing with the GPIO, let's just fix this behavior. So it was in the timer, I think, and yeah, there is int enable, int force, and probably we have this logic somewhere. Yeah, there was a method. Yeah, so basically we just need to change it, but let's add a unit test for it. So alarm timer spec. And as usual, tests on the left, timer on the right, and so yeah, so basically we want it should generate an interrupt if int f is 1, even when the interrupt is disabled, or when the int e bit is off, or maybe is 0. All right, so we have this we have this int r, which is the int s, the interrupt status is 0, and then if we write and int e should also be 0, because we haven't we don't even need the alarm actually. And then if we write to int f, let's say 4, then yeah, we need to define INTF. So INTF is INTF. Yeah, there are too many of those, so let's find, not here. Where is that? Alarms. Timer. Where are you? 3C. Yeah, right after int C. So int, and then we expect the int status to be just, you know, 4. And right now it's interrupt the corresponding interrupt. It should be 1. Okay, and now obviously it doesn't work because we implemented it the other way around. So let's fix the implementation as well. So this should fix the implementation, and now this is green as well. Cool. So yeah, so fix timer, close this one. Int f has should have priority over int e. C, and then where is that comment? This one. Or maybe reference. This is the reference. So yeah, sometimes it's just easier to ask rather than testing it yourself. Cool. So that's another small fix. Another step towards better implementation, better simulation. And let's take a look at a list of open issues. So yeah, that's something we haven't done last time, pausing the timer and letting you set the timer value. But for now it's a low priority because we haven't seen this used in the wild. But if anyone wants to try to take this, then you're welcome. And then there are like 2 issues from 2 weeks ago where Valerio, actually this one is where Valerio found a discrepancy between the silicon and the emulator, and we need to investigate it. And that's one that I found. And this one is also interesting, the extra addresses for XA Flash and SRAM, but so far I haven't found anything that uses this. But if you do, let me know and we'll probably prioritize that. And now we are going back to the GPIO plus interrupts. We started it last time with the SIO. We still need to do the control status registers and the pad registers, so there is still some work to do. Before we do that, I remember Nikati. Hey, Tomasz. By the way, hi. I just seen your hi now. Nikati asked last time, I think it was Nikati who asked for it, whether we got MicroPython to run. So last time it didn't work. So, you know, I just want to real quick test if we somehow got lucky and the recent changes, I mean, it's good to be optimistic, and they emulator run. So if the recent changes, the spinlocks and the integer divider made it possible to run MicroPython. I think last time it was stuck in some kind of loop or something like that. So let's try that. Are you ready? Drum roll, please. Not very good at drum roll, so it seems like it doesn't work. It's stuck on an SEV loop. What's going on? WFE. Yeah. So yeah. Oh, wait a second. What is that? Traceback. That seems like a legit output. MicroPython V115117. that seems cool, and this seems like a prompt. So yeah, that's exciting. It seems like it's sort of working, waiting for event from probably user input from the user. So yeah, that's cool. Yeah, we can probably make a more user-friendly version just to celebrate this moment, like another script that run MicroPython, and this one, instead of printing UART sent, will just process.stdout.write, and then guess new int8 array with this value, and then we should probably get the output in one chunk instead of one character per line, which will be easier for us to read. And yeah, what happened here? Oh, we are still running the old script. Let's add another script to run the MicroPython. So we have start. Let's have maybe we'll call it MicroPython run, like we have an emulator run. Start MicroPython. So hey Punith, MicroPython run, and then let's npm start. And just for the sake of not seeing all this console output for now, where is the RP2040? We have those WFE console logs, and I think there was also a bunch of SCVs, right? So let's just comment them out for a moment, and we should probably have a better way of disabling this debug output. Yeah, so it takes it a while to start. Oh yeah, I need to start run start MicroPython to run the correct script. Cool. So yeah, you can see that it has some OS error. My guess is that I'm not sure what is this boot.py. Let's try to take a quick look at that. So that's the MicroPython source code, and I guess there is like boot.py. That's for the ESP32. Yeah, just out of curiosity, instead of doing what I should, which is yeah, this is the boot, which is the GPIO. I'm just digging into MicroPython code. Anyway, you can see that it said it failed on line 11. So it's like when it tries to initialize the flash, and that makes sense because we still haven't implemented a flash. But it's cool. This means that it actually interprets this code and gets to this line and sees this error, and then just goes to the prompt. And obviously we can't type anything yet because we still haven't implemented Rx for the UART. Yeah, but I don't know. I mean, yeah, I think we will probably go with the GPIO for now. That's a cool thing to see the beginning of MicroPython. And once we finished with GPIO, or maybe we'll just have a spontaneous live stream later this week where we will just add the UART RX and try to get to working MicroPython prompt. So for now, let's just commit this. So we added this and added this, and yeah, we don't need the change in emulator run. And for now, let's not commit those because we probably, you know what, let's just do it now. So let's do let's add a variable. Maybe we'll call it so many variables. Debug missing or log missing instructions, which will be true by default, but then in the MicroPython, we can set if to false, this.log missing instruction, then only then print WFI. Same goes for yield. And we also have this one. And I don't know if we have other console log. Yeah, for SEV. Yeah, and yeah, console.log. And there is probably a better way to do it, which is having some kind of logger and then sending those messages to that logger. And we might do that at some point, but for now, I think that's a good enough solution. So here we can say mcu.log missing instructions equals false. Just one more time to see how it works, and it doesn't bombard us. Yeah, cool. So cool to see the MicroPython prompt. Cool. So feed demo, add MicroPython project. And just a quick reminder, if you want to run it yourself, you will probably need to compile MicroPython from sources, because we don't have the USB UART, and I think I have this. Yeah, I had to, no, that's for the debug. I had to set this to 1, so to enable the UART REPL. So we'll have this UART REPL. But if you just want me, you can open an issue and I will just upload a precompiled hex if you just want to play around with it. Cool. So let's commit that for now. So you will be able eventually to play around with MicroPython as soon as we have USArt RX. Okay. Oh, by the way, there is one more pull request to use the boot ROM from the real Pico, and there is a discussion about updating GDBdiff to read the memory from the like to extract the boot ROM from the actual device you are testing against, so you won't get any differences. Like you won't get false positives for differences because of boot ROM differences. And we'll do we have a very lively discussion here about potential improvements to GDBdiff, and maybe we'll do it in a side stream at some point this week or next week. But right now, let's go back to GPIO. Let's see how much we can get. I hope to have a usable implementation today, so we'll be able to run Blink and other stuff. Cool. So yeah, last time we implemented the SIO part of the GPIO, and yeah, there is still to do here, but basically there are like all those registers you can write to change the status of the GPIO. And I think after we did that, we also implemented a sort of abstraction that handles a single GPIO pin. So there is like get value that returns the value of the pin, and then it looks at the SIO, and then it determines whether it's like output, then it says it's high, otherwise it says it's low. And we still need to account for pull-ups and pull-downs, and there is like this thing where GPIOs can be set to different functions. I think it's section 2 point something. 19 function select. So basically only if the pin is set to function number 5, we should reflect the we should do this. This should only happen when the GPIO the pin is set to the SIO function. So I think the first thing we are going to do now before moving forward and adding the missing functionality is implement those 2 other peripherals. I think they are outlined here. There is like the IO bank 0 base, and then there is like just below that somewhere QSPI IO QSPI base, and then there is I think there is also PEDS something. Yeah, so there is like a PEDS peripheral. So yeah, PEDS bank 0 and probably PEDS QSPI. Yeah, so we have all those 4 peripherals that control the GPIO, and let's do them. So let's add PEDS peripheral, and I think the other one was called just IO. IO.ts, and then we can also, like, there are 2 GPIO banks, so we can probably yeah, I think for now I'm not sure if we should do the QSPI now, because they are not really useful for most use cases. So I think we should just do the bare minimum so we don't get warnings, but other than that, don't worry about them too much. Let's take a look at this IO bank 0. So there is like those registers that control them. This is here. So there is like a status and control register for each pin, and we should do that. And then there are like interrupts. You can see the same pattern as we had in the alarms. Row interrupts, enable, force, and status. And then it's also by processor. And right now we only have 1 processor, so we don't need to worry about proc1 and about dormant. All right, so let's start implementing this peripheral. Yeah, we can probably call it we don't need all of that, just this and probably this. So that would be RP, I think it's called RPIO, yeah. All right, and then we don't need a clock, just the skeleton of this. So and then here, yeah, we don't need the rest of the functions. All right, and then we can probably yeah, we can start doing this. So for every GPIO we have like this status, which is, yeah, it has a bunch of bits. So probably the status, and then the control, which is overriding the IRQ, overriding input, overriding output, function and function select. Okay, and this is read write. So yeah, I guess for each IO pin we can then store this control value. So control number, and the initial value will just be always 0 except for those lower bits, 1F, which probably means it has no function. All right, and then for the status, we'll see in a moment how do we generate that. But at least for the control, we can, whenever we are reading, we can say, so yeah, maybe I'm thinking how to do this. If we can do it generic for the two banks, because there is like the QSPI bank as well, which is kind of similar, I think. Probably a different peripheral will be a better way, because there are like differences in the number of interrupt registers and etc. So yeah, so let's just take a note of the latest GPIO control. So const GPIO CTRL last is just this is just the address of the last the offset of the last control register. So if offset is less than or equals this last register, then const. So you can see like these registers, like the GPIO index is just like dividing this by 8. So offset GPIO index is just offset shifted by 3 bits. So that's the equivalent of dividing by 8. And then if it's like if this bit is 0, then it's status. Otherwise, it's status. Then offset. So actually, we can do it the other way around. So if this bit is set, then it's control. Otherwise, it's status. And let's convert this to Boolean. Cool. And now if so we can return if is control, then we just return this.rp.gpio at GPIO index dot control. Yeah, maybe we can just create a helper and method, because we'll need the same logic in the right. So let's call it get GPIO or get IO from offset and offset number, and then we just do this, and then we return this. So instead of doing this, we can do const GPIO offset, and then just GPIO.control. Otherwise, we need to figure out the status. Let's make the GPIO class take care of that. This. Maybe get pin from offset. That's get pin from offset, and then we can create this status here, and for now it will always be 0, but we need to figure this out to figure out the correct status. All right, and then for write we have a similar logic. So we do want to switch. So if this is like inside this control section, then we just call the get pin from offset, and then if is control, yeah, we can probably do something like just return an object, so we'll have the same logic reused here and there. So if so now we can say GPIO and is control and paste it here as well. If is control, then GPIO.control equals value. Otherwise, we can't write to the status. It's read-only, so we don't need to worry about it. You see, everything here is read-only, so no need to worry about this. Cool. Okay, so this is the implementation of the some of the IO bank. We still need to do this, take care of the interrupt registers, if I'm not wrong. Yeah, all those interrupt registers. But we already took care of those status and control bits. Valeria, why do you say ouch? What happened? Okay. And then, while wondering why Valeria said ouch, let's go to this RP2040, or not. Yeah, I wanted to go there and just plug this peripheral. So yeah, so basically instead of this, just we'll use RPIO. And then let's also do the pads. If I remember correctly, the pads peripheral is where you define the pull-up registers and all of that. And yeah, let's see. So we have RPIO, and then there is also RP pads. And then let's see how that works. So there is probably here this list of, yeah, so there is like a voltage select, so we can select the voltage, but you know, it's a simple read-write register. We don't really, I don't think we really need to do anything about it right now, but let's just implement it. Const or let voltage, or just voltage select. By default it's 0, so then we can just have this. Oh, Opera got frozen. It happens, I guess. So voltage select is at offset 0, and then we can do switch offset case voltage select return this dot voltage select. It's read write, right? Yep. And then here case that was voltage select, this dot voltage select is value, and it's just a single bit break. All right, and then after voltage select we have all those GPIO and SWD pins, but I don't think we should care about them too much for now. So yeah, we probably have a similar thing that we have, like this pin from offset. So let's have GPIO first, which is the first register, it's 4, and GPIO last, which is at 29 is the last, 78. And then we can say if offset is within this range, first, and offset GPIO last, then this dot get pin, we only need the pin itself. We don't need we don't have this thing where we have like status and control, and this is like jumps of 4, so we need to shift by 2. So and then if GPIO GPIO pad value, and we'll implement that in a moment. And then on the other end, on write, I think those registers are read write, yes. So if we are writing, then GPIO equals this, and GPIO.pad value equals value. Okay, so yeah, and then we have all those two registers, SWCLK and SWCLK. D register, which seems similar to those other registers. But yeah, right now I don't want to worry about them. I don't think most people would use those debugging pins as GPIOs, because then you lose the ability to debug, I guess. So we don't need to worry about them for now. Cool. So that's for the I/O and for the pads. We still need the interrupts in the I/O, and we still need to implement this pad value and the status in the GPIO pin. So let's start with just setting the initial value. We can see it's 0, 1. Let's just copy from the datasheet. So 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, right? 1, 1, 1, 1, 0, 1, 0. Oh, that's no. So that's those two registers. They have like a different logic. So the usual pads registers, they have 0, 1, 1, 0, 0, 1, 1, 0, different default, 1, 1, 0. All right, and now we can probably have some utility methods. So users of this class will be able to query the status of the spin, for instance, get. So we have here like slew rate. I'm not sure what's that, but get or is slew fast. Return this .pad value. Just let users of this class get quick access to those values. So is slew fast is Schmidt enabled, so that's the next bit, and then we have pull down, pull up. So I think pull down is the next one, right? Pull down enabled and pull up enabled. That's the next one, and you can see that by default the pull down is enabled, and then there is like a drive strength. So get drive strengths, and then we need to return those 2 bits. So return this .pad value shifted by so we need to shift it by 4. And return just the lower 2 bits. Input enable and output disable. So get input enable, return this pad value, and that's the 6 bit. So yes, this is it's 0. So yeah, so that would be 40. And to Boolean. And finally, there is output disabled. Get output disable. Okay, so now we can already, with those new values that we read from the pad register, we can already thicken our implementation that calculates the value of the pin. But before we do that, like for instance, we can, if there is output disabled, then we can just return that the pin doesn't have like, ignore this and then account for pull up, pull down. But before we do that, let's also take a look at this control and status and see how we can do them. So list of registers. So let's start with control. So it has a few bits. So let's start with the lower one, function select. So get function select, and that will just return this control, the lower bits. And then we have like those functions, and this is like the default. And then there is like output override, output enable override, input override, and IRQ override. All right, so let's do them. Get output override, just return this dot control, shifted by I think 8, yeah, 8, and then take those lower bits, 2 bits, and then there is output enable override, and it's just the same, shifted by 12 bits, and then shifted by 16 bits is input override, right? Input, yeah. Input override, and finally we have RQ override at bit 28. So this was 16, I think, right? And then yeah, 28. IRQ override, so 28. Cool. And now we have yeah, there is also the status. So we have the input signal to the peripheral, input signal before override, output enable, output enable, output signal, and output signal. And there is interrupt before and after. So I guess these are all values we should store in a way or some way or another. So when we want to calculate the value of the pin, we should take all of those into account. So let's try to do that. So first of all, this is like if we don't have if we have no output, then we can ask if this dot pull down, then we just return GPIO pin state pull down, and the same goes for pull up. And I guess that I don't know what happens if both are enabled. I guess I don't know if there is anything that yeah. They say or a pull down, so maybe enabling one. Voltage select. Yeah, I'm not sure what happens if you enable both. Maybe they are mutually exclusive or something like that, or maybe you just get in-between level, output level. That sounds strange. But anyway, I don't think we should worry about this right now. If anybody wants to check what happens when you enable both, that would be an interesting experiment. Maybe to do check what happens when we enable both pull up, pull down. Okay, and now right now we get the basic output enable and output value from the SIO, but I don't think that's the correct way to go about it, because yeah, first of all, I mean, because we have this function select, so it really depends which peripheral we are connected to right now. What we are going to do is probably have some kind of table where peripherals can let us provide their values for us, or maybe a callback. Anyway, status is read only, so we don't need a variable for it. Let's just create a getter for it. So get status, and it just returns the status value, register value for the pin as outlined. Where is that? That's 2.19.6 in section of the datasheet, just so the users will know it doesn't really, it's not really useful for the end users. The value is probably more useful than the status. And let's try to return this sort of status. So there is like before overriding and after overriding. So we need somehow, let's return 0 for now and to do, and I will just copy it so we won't have to look for it. So just copy the relevant bits. And then there is like so it's always like after override and before override. And then there is like 17 this one, and the rest are just zeros. That's here, that's here. And finally, we have like 9 and 8. And then a bunch of useless bits. So outpad. And there is like out from Perry. All right, so there should be a value for a way to for the user to specify the value for that pin. So for instance, if it's connected to a switch or something like that, we want to give the user an API to say this was now externally driven high or low. So we can have like set value value boolean, and then this dot row value equals value, and then let's have this row value, which will be false by default, or row input value. Okay, and then we can already like start doing this status. So we can that would be in to Perry is just if this row input value, then it's like this bit, otherwise it's 0. And then we can probably so there is like this logic here where we can invert it or whatever we do. We can probably implement it in a getter. Get that's into Perry in from pad. That's the row one. In from pad, that's the row one, sorry. So and then we can probably have this input value, and this will be after like those overrides are applied. So we are just switch this input override. So depending on the input override that the user has configured, let's see how the input overrides work. I think the input override is inside, that was inside the control, right? Input override. Yeah, so many features, small features to take care of. That was here. Yeah, so 0, don't invert, 1, invert, 2 is just low, and 3 is high. Okay, so case 0, return this dot row input. 1 would invert it, and 2 will always return false, and 3 will always return true, right? Yeah, and I think we have this logic in a few places, so we can probably have where did I go there? We can probably have a function that does this. So small function that we'll call function override value boolean, override type number, and then just use that. Maybe we'll call it apply override. Apply override, and then yeah, just takes value, and here it just takes override type. Okay, and now we can use it here. So turn this dot apply override of this dot raw input value. Actually, we can probably just cache this value equals false, and then whenever we no, let's not cache it right now because it depends on the control as well. So we can probably optimize it later. So just apply override to the input value and this dot input override. Yeah. Override. Yes. Okay, cool. So now we can sort of return const into Perry, implement this as well. So that would be input value. If it's true, then that would be shifted by 19, otherwise 0. And yeah, let's have another like interrupt equals false. Similar logic for interrupt. So const IRQ from pad is this dot interrupt. So if it's interrupt, then that's 24. Otherwise, by the way, do we need parentheses here? No. Cool. So that's IRQ from pad and IRQ to proc. This dot. Let's have IRQ value. Maybe let's change this to row interrupt, and then IRQ value is just if it's true, then that's 26, and let's implement IRQ value as well. Get IRQ value is just applying override of this row interrupt with IRQ override. Yeah, and we are almost done with status. Yeah, we just need to return bitwise OR for all of those. In from pad and into Perry, and then we have a few more. Let's just sort them by value. Okay, so we have const out to pad this dot out to pad is after, so this dot output value, and we'll have that we'll create that in a moment. So if we have the output value, then it's 13, and then we have the row output, which is out from Perry, and that's 12. So out to pad, out from Perry, and yeah, writing test to this is going to be so long. Out to pad, oh, that was OE to pad, out enable to pad, and yeah, output enable value and row output enable, or you can just call it output enable. And this dot output value, so that's the out to pad, that's at 9, and out from Perry is just row output value. All right, and we are going to implement those in a moment, but first of all, let's finish this. So we have here OE to pad and output value, no, OE from Perry. Cool. So we did this gigantic status function, and we now need to add row output value and row output enable. And we are going to read those ones from the SIO in a moment, if function is like set to the SIO, but we'll get to that. First of all, let's have those getters, output enable and output value output, and then we are going to apply override and output row output enable, row output value, and these dot output enable override and output value, or is it just output override? Yeah. Whew. Yeah, that was a long one, but yeah, finally we have this status implemented. And now, instead of in this function that returns the value, instead of reading from the SIO, we are actually going to do something else. We are going to just read this dot output enable, and let's just copy it because we'll need it in a moment. And here it's going to be this dot output value. Cool. And now, and we don't need the bit mask for now, and this one as well. And now this code is sort of generic. It will work with whatever peripheral will plug at the other hand. And then, yeah, we would probably need to, like for now, we will at least have the SIO peripheral, and we will probably start working maybe today, maybe next time on the PIO. So we'll have in the simulation we'll have those 3 peripheral, and I don't know if we will dive into implementing all those like peripheral, like those protocols in like the actual protocol implementation. But even if we don't, these values will still be valid when you use SIO PIO 0 and PIO 1. Cool. So yeah, now we need to this is no longer with it's all now without any errors, but now we need to plug it back to the SIO. So what I'm going to do, instead of using those variable for raw output enable and raw output value, they will actually be getters. So yeah, let's do them here. Get raw output enable, and this dot peripheral dot raw output enable and return, and the same goes for raw output value. And yeah, or we can probably for now do something like this and later on improve it. Switch this dot function select. So right now we only support, so function select is like one of those functions, and right now we are only going to support SIO, so that would be number 5. So export const function SIO equals 5. So case function SIO, then we have this thing. And we just return this, and the same logic, otherwise we just return false. And let's do this boolean, and same goes for raw output, but just reading from GPIO value, I guess. Okay, cool. Not false, return false, and same here. So by default we return false. So yeah, so why isn't it happy about it? Oh, raw output value. Yeah. So yeah, so now this code is more generic. It will be if we want to plug. So for all the peripherals other than SIO, for now, the output will always be disabled, and only for SIO it will return the actual output values. But once we get PIO, we can just add another statement here and plug it in. All right, and yeah, we also need to add a way to listen for value changes. That's going to be a bit no, it shouldn't be too hard. We should just have some function that we call from the SIO whenever we update the value for the GPIO pin, or whenever we update the control value, and just check if the value has changed. Cool. So let's go back to the SIO, and I think we are still missing like the input. Yeah, so for GPIO in, we should just, go all over the GPIOs for this dot, for let I0 I const GPIO this dot RP2040. So I GPIO dot length I plus plus GPIO dot at I dot input value. So if this is true, we just set this bit in the result dot result or equals 1 shifted by I. So let's call it bit or GPIO index. Yeah. Cool, and then just return the result. So that's for the standard GPIO. For the high GPIO, I don't think we should bother right now. we would probably need, maybe we do have, no, we would probably need to create another array called, instead of GPIO, called like, yeah, we can probably do it. It's not too much work. Let's have, instead of GPIO, QSPI, and I think that one has less pins. Let's see. List of registers. So there is like GPIO, and then for the QSPI bank. Yeah, but where is the QSPI base? Yeah, so there is like 1, 2, 3, or yeah, there are like 1, 2, 3, 4, 5, 6, I think, total pins. Yeah, 6. So there is goes from 1 to 5, and let's also give them names. So this is like SCLK, SS, and then SD0 to SD3. And then here we can add also only name equals index to string. So by default it just equals to the index 0 to whatever, but for those pins we'll have proper names. And then here we can probably and that's very partial implementation, but just so we have this SIO without this to do, we can probably do the same, but instead of, let's put parentheses here, curly brackets, we can go over QSPI, do the same. All this QSPI index. Yeah, just have the same logic for the QSPI. Yeah, so I think in terms of SIO, the SIO is pretty much ready. Like it has all the code to implement the GPIO, and now we just need you know, to make sure that there is a way to listen for value changes. So the user, instead of having to check the status of each pin after every single instruction, the user will just be able to, you know, let's have add listener that has that gets a callback, which will be GPIO listener or pin listener, and remove listener, GPIO pin listener, or maybe we can even simplify the API. So add listener will just return a method that will remove the listener, and then we can have like a set of listeners. So listeners, just a new set of GPIO pin listener. And then let's define this export type GPIO pin listener is just a method that gets new value, or yeah, the value is GPIO pin state. And it doesn't return anything. We can probably also give you the yeah, the old state. Maybe state and all state are better names. Now adding a listener is just this dot listeners dot add this listener, and to remove them just this dot listeners dot delete the listener. Oh, the callback. Cool. And now we only need to call the listeners whenever this value changes. So we can add a method that will do that. First of all, let's set this one to read only, and this is private, and these ones can't be private, but I think these ones can. They can't be private because we use them inside the IO and the pad, so we don't want them to be private. All right, and now, yeah. So check for updates. And then we want to check if value has changed. So let's have another variable that will store the last value. Value is this dot value. Basically, it will just have input at or input pull down at the beginning, because by default we have pull downs. Yeah. And then, so if this dot value doesn't equal this dot last, or let's copy the last value. So this dot value. So if it's not equal, then we are going to update it first. So any of the listeners will see the new value. Yeah, we can probably just read it once. So if this dot last value equals value, and then for const listener of these dot listeners, listener with the value and the previous value. Cool. Oh, it equals this. Yeah. Okay. So now the only thing we need to do is call, maybe we'll call this, instead of set value, set input value, to make it clear that it sets the input value, and this is actually the output value. Okay, so now we need to call check for updates whenever we update something. So that's basically whenever we update control, whenever we update the pad value, which could affect the value. So we can do it in this class, or we can just do it when we update them, like here. So in this case, we can just call GPIO dot check for updates, and same goes in pad. GPIO dot check for updates after updating the pad value, and inside the SIO as well, whenever we write to some GPIO here, we also need to check the value of those GPIO. So we can probably have a list of GPIOs that we updated. So let's const prev GPIO value is this dot GPIO value, and const prev GPIO output enable is this dot GPIO output enable, and then yeah, don't we have a default here though? Yeah, okay, we don't. Let's add a default, so in case right uint, oh, there, this is like, yeah, it's not inheriting from Peripheral, right? So we don't have a superclass that will print errors in case we are writing to an unimplemented address. So let's just add the warnings ourselves. Right to invalid SIO address value, and value to string 16. Okay, and then here we can just do Yeah. So here we can just do if this dot GPIO value is different from prev GPIO value. We can actually do something like that to figure out which pins we should update. Const pins to update. We can just XOR them, so GPIO value or XOR prev GPIO value to see which pins have changed, and then we can bitwise OR it with. We don't care what changed, we just care that something has changed. So GPIO output enable with prev GPIO output enable, and if this produces anything, if there is a value pins to update, then we can just go over the pins. This dot rp24 this dot rp2040. So GPIO.lengths, and if pins to update, if this bit is set, then just GPIO at I dot check for updates. So this will just make sure that GPIO index, much better. Yeah, this will just make sure that whenever the code writes to some changes some pins, it will also call check for updates. We could have called all the check for updates in all the pins, but since it's doing like a bunch of calculations, then that would probably make sense not to do it. Whenever we update something in the SIO. Cool. So I think we have a very basic implementation. I mean, it's probably a good one, except for we are missing the interrupt. So first of all, I'm not sure. I think we still haven't added this to the RP2040. So yeah, where is that? Pads. Yeah, so this should be RP pads. All right, and now let's do a quick check with blink. So we got blink, right? Yeah. So blink.hex. And let's see what's going on. It died. Horrible death. Can't read pad value of undefined. How comes? Ooh, yeah. We should probably subtract the offset of the first pin before doing this shift. Otherwise, we may get out of the array bounds. Okay. Yeah, let's disable loggings here. The logging mcu.log false, so we don't get bombarded with those WFE. But in general, we shouldn't see any output right now because we still haven't attached any listeners. But now we can GPIO, I think 25 dot add listener, and then state console log GPIO 25 and the state. Let's see how that goes. Okay, so yeah, you can see it started with 4, and 4 probably means it's a pull down because GPIO pin, because yeah, it's the 5th value. So it started as pull down, and then we can probably I think there is a way to actually ask TypeScript to, if we index this by the state, we get the string representation, which will be a bit more useful. Yeah, so it starts as pull down and then it goes low, high, low, high, low, high. Looks pretty good. So yeah, that's pretty cool. We have Blink working with the new GPIO system. And before we write some tests and check for bugs, probably do the interrupts code as well. There is like those annoying pads QSPI. So let's just quickly implement these QSPI things. So let's have pads QSPI, which will be quite similar to pads, but we'll do the so I think they also have like yeah, there is like also voltage select, and then there is like just 6 registers here. So that would be QSPI and QSPI pads. And yeah, here instead of GPIO it should be QSPI first, probably one more below, and this one, yeah, we can probably yeah, we can probably just make one that will take parameters. So just QSPI read only QSPI is by default it's false, and then let's have const QSPI first is the same, const QSPI last is this, and then yeah, this so if this.qspi, else we are just returning the GPIO pin, otherwise that would be QSPI, and we actually don't need yeah, we can GPIO first and QSPI first are equal, but let's just keep them. Maybe we can do it like that. First register is this.qspi, or first pin register, first pad register. If this QSPI, then QSPI first, otherwise GPIO first. Same here, it's all private read only, and this one is the last, and QSPI last, QSPI last, and then just this first pad register, and same goes here. And yeah, I think this yeah, just fix this one. All right, so now this should be generic enough to just reuse it here. So we can just create yeah, maybe instead of yeah, that was QSPI base, maybe instead of using a boolean, we'll just use enumeration or a string value, so just to make the code a bit more readable. So export type bank, IGIO bank, it could be QSPI or GPIO 0, and then read only bank IO bank, and then if this dot bank is QSPI, then this, otherwise that. same here, and same here. This, yeah, all right. Cool. So now that should remove this annoying warning about this unimplemented peripheral. Let's see if that helped. Yeah, we should probably not assignable. Why not? Oh, bank 0, or how do they call it in the code? Bank 0, yeah, bank 0. So here it should be bank 0. Yeah, okay. So let's see if these annoying warnings, first of all, it still works, that's great. And yeah, those QSPI warnings disappeared. We still have a few about this watchdog and TB-man that we need to address, and those strange writes probably trying to speak to the QSPI flash chip or something like that. What's this address? Yeah, the SSI is probably yeah, appears on the QSPI pins. We'll get to that one day, but for now, those warnings about QSPI has disappeared. Yeah, we can probably try to implement this one as well, the IO QSPI. Let's see if it's not too complicated, we'll do it. Otherwise, yeah, I think we should first do interrupts and then worry about this one. So interrupts, how do they work? Yeah, so interrupt. So an interrupt can be generated for every GPIO in 4 scenarios: level high, level low, edge high, edge low. They are not latched, so these are like the level. So as long as the interrupt is active as long as the pin is high or low, and the edge interrupts are stored in the inter register, and there are enable, status, and force for each of the processors. Right now we are only interested in proc 0, and they are like, yeah, so for each bank to each processor there is like interrupt. Cool. So yeah, let's try to do that. So first of all, let's go to the GPIO pin, and then we already have like this row interrupt and IRQ value, right? Which so what, how do wait a second, I think there is a register that controls the interrupts probably. Yeah, there is like enable, and then there is like for each GPIO there are like 4 interrupts that we can enable, and I guess yeah, we probably need to have all of those interrupts, and then yeah, we can use that too. So let's have flags to store those interrupts. So IRQ edge high, and I guess by default they are all false. IRQ edge low, IRQ level high, and IRQ level low, right? Okay, and now we can update row interrupt after after we set the input value. So I think I'm not sure about it, but I think the interrupts are probably after the not a row input value but the processed input value. So if this dot So if value, or yeah, if this dot IRQ edge high, so if value, no, let's do it like that. If we need to IRQ edge high and value, then yeah, we need to probably have like enable for each one and the interrupt status. So IRQ edge high enable, or maybe we can just make our life easier by IRQ enable mask and IRQ status mask. Okay, and then let's just define consts for IRQ edge high is this one, like 4 bits that will represent those. So edge high, and then there is edge low, and then there is level high and level low. Okay, and oh, Valeria said great about something, not sure what. Maybe that we got the GPIO to work, or remove the extra console log chatter. Okay, so IRQ, yeah, so we have IRQ enable, I guess, and yeah, IRQ enable mask and IRQ status, and by default they are both 0. And then we can do if IRQ enable is this. Okay, so if this dot IRQ, or yeah, I think we should update the interrupt status regardless of the we should update the interrupt status regardless whether they are enabled or not. And then enable is just like whether we generate interrupt out of that. So this dot so if value, or we can say this dot yeah, so if value, then it's rising, and this dot IRQ status is yeah, so IRQ status is IRQ edge I, if not value, then IRQ status is or edge low. So those are like latched interrupt, they need to be cleared. And then this dot IRQ status, if it's high, then we also enable the level high and clear the level low. And yeah, and the opposite happens here. Maybe we can just else. So it's also IRQ level low, and then we need to clear IRQ level high. And this is just the IRQ status. Now we also need to have like force, because we know we have this force. So we have like so IRQ force mask equals 0 by default. And then yeah, I guess row interrupt should just be calculated from this. So let's add a getter for this. So get Otherwise, like, it will always be true if we don't like take enable and force into account, I guess. So return this.irq status and this.irq enable mask, or this.irq force mask, and we need to convert this into a boolean. Okay, cool. So we probably got a basic mechanism for interrupts, and now we also need to if this dot so if this dot interrupt IRQ value, if there is an IRQ after updating and checking all of this stuff, we need to tell the processor there's been an interrupt, right? So we need to this dot RP2040 dot set interrupt, I think, and then we need to know which IRQ we need to set. And yeah, that's eventually we will need to have those per processor, I guess. But for now on, we can just hard code that it's like this IRQ, where is the interrupts. So it's like the IO IRQ bank 0, I guess. Oh, there is IORQ and SIORQ. What's the difference between them? IORQ. So what's the difference between SIORQ and IORQ? SIORQ. Yeah, I think the SIO is like for those FIFOs that we still haven't implemented, so it's not related. So we should just, generate IORQ and the states per processor. So maybe we should just send it to the right core, but right now we only have one, so we don't have to care about it too much. And then we can define this constant. This is like 19. Then we can go back here and this dot RQ value, just set it according to the RQ value, or why is it undefined? Oh yeah, we should probably have like a default value as well. I mean, it shouldn't happen, but just so TypeScript is happy. Yeah, let's just have it here. Just a fallback if nothing matched, which shouldn't happen. Maybe we should also apply override received invalid override type. Yeah, just in case. It shouldn't happen, but if it does, we want to know that something went wrong. All right, so we had a lot of code. So yes, yeah, I think this should probably do the trick. We just need to go back to this IO class and now just update those registers. So let's see. So where were we? GPIO list of registers. Oh, wait a second. There is a bug, a small bug here though. We should set the interrupt whenever the IRQ value is updated. We should look at all the pins and according to them set the interrupt. So yeah, maybe we'll have prev IRQ value is this dot IRQ value. So if it changes, only if it changed, this dot IRQ value isn't the previous value, then we need to go over all the pins and update the interrupt. So CPU interrupt is just this dot RP2040. Maybe we'll just have update GPIO interrupt or IO interrupt. Okay, and then the CPU will take care of that. So yeah, let's just move it below. So that's probably after send interrupt and check for interrupts. Yeah, so we can have this, and then this just goes let interrupt value is false, and then for const this dot pin of this dot GPIO if pin interrupt IRQ value interrupt value equals true, and then just update this interrupt with this value, and we can move this constant to the other file. All right. Yeah. Okay, so at this point, this is probably the implementation of the interrupts should take into account all of the pins. And now let's see. Yeah, we need to implement the register. So there is like row interrupts, interrupt enable, force interrupts, and status, interrupt status for each of the interrupts. For proc 0, and we are not going to enable it for the rest of the processors. So yeah, we can probably have this register. It's in IO, and then const. So that's 100, right? And then there is like this 3 of those, and then there is int f. So there are like 4 of those, and same goes for int e probably, or yeah, that's int f, and then there is int s. So there was also one with a row interrupt. So that's 120. So yeah, add inter, yeah, at F0. Yeah, row interrupts aren't per processor, obviously. So that's, yeah, row interrupts. It's at F0. Okay, so let's implement reading and writing from those registers. So maybe we'll have another helper method for that. So if offset is in this range, like offset is less than, yeah, we have it here. Yeah, let's have the proc one so we can know where the proc 0 ends, or maybe we'll just call it S3, the last register. So that's probably 120C, right? Yep. So if we are in this range, then we can take we can find a GPIO by just looking at the offset at the at this lower 4 bits. So let's have another get interrupt register pin that has this offset, and then const GPIO index. Yeah, actually we have a bunch of pins, so we'll have it's pins, or yeah, we can have the first and the last indices probably. So we can say register index is just offset, take the lower bit, so like take these lower 4 bits, lower nibbles, and then so for the first one, for instance, that starts with int S0, it starts with, let's see if it works that way for all of them, like for int R. Yeah, so for int R0, yeah, it starts with GPIO 7. So yeah, it's always 8 registers. So maybe we don't need a function. So basically, it's just the register index is just taking the offset and I think multiplying it by 2, because yeah. So for instance, for this offset, which is 0, it starts from GPIO 0, and then for this offset, which is 4, it starts from GPIO 8, and this is 8, it starts from GPIO 16. So basically just taking this nibble, multiply it by 2. We don't even need that. Yeah, we can probably remove this function. It doesn't do a lot. So yeah, not here. So const start index is just this, and then const register is offset. We just want to take the higher bits, so now we can just switch on register, and then depending on the register we can or maybe we can do it the other way around. For let index of is running from 8 to from 0 until 8, so going over all the GPIOs that are controlled by this register, so over all 8 registers, GPIOs, and then const GPIO this.rp2040.gpio. Yeah, we can probably, GPIO is just this. And then we can probably say const pin is just GPIO at index plus start index, and const pin value, just, you know, the relevant bits for that pin. It's just value shifted by pin times 4. So we want to discard, so if it's let's go up here. So for instance, if it's pin 0, we will shift it by 0, so get those bits. If it's pin 1, we'll shift it by 4, so get those bits. So do it it like that, pin index, and we only want the like 4 bits, and then depending on the register, that would be register. So if it's int R0, we return this dot. Oh, wait a second. No, we need to go the other way around. This is read, not write. So yeah, let's actually copy this to write, because this is more or less the logic for writing, and then we'll switch to reading. So yeah, so if it's int R0, then this dot pin dot interrupt row RQ. Yeah, actually we need to do this because I don't think we have implemented this yet. And then int R, and this is like it's a pretty complex one. It has write clear and read only, so we only need to account for those write clears. But for the other ones, proc0 interrupt enable, then we can say pin dot interrupt enable IRQ enable mask is just pin value, and same goes for forcing, force mask. Okay, and here and I think for status we don't actually need this, right? For status it's like read only. That was proc0 int s. Yeah, I think it should be, yeah, it's read only, the status. And for int r, we should probably yeah, well, to do it in a moment, or let's pin dot update IRQ value, and let's give it a pin value, and then it will only look at those where was that, proc int R0. Yeah, it will only look at those 2 higher bits here, like bits 2 and 3, and use actually we should instead of looking at value in this case, we should look at yeah, there is like this row write value. We had it last time with the timer. So for write clears, we should look at the row write value. So instead of doing this, we should probably in this case, just in this case, let's have a plain row write value. So yeah, it's getting a bit complex. So in this case, we just need to do this, and then in the pin, let's have this method. Probably somewhere here. I don't know where to put it. Maybe after check for updates. So value number, and this is basically write clear, so we can say if value, and I think that was yeah, only the edge can be cleared. So if this bit is set, and this dot row interrupt, yeah, and so if this is set, and this dot row interrupt, and this bit is also set in the row interrupt, and we want to clear it, and we want to we know that we have changed it, so we also want to update the IO interrupts. Why isn't it happy about it? row interrupt is boolean. It's IRQ value, I guess. IRQ status. Yeah. So IRQ status. So clearing this one, and the same goes for the edge height. So if it's if we should clear it and it's set, then we clear it and updating the interrupts. All right, so we no longer need to do this because we have it. Yeah. And then we need to finish reading. So if we are just looking at the row interrupt status, yeah, we can probably do something like that. Instead of having pin value, let's have let result equals 0, and let's go the other way around. Let's go from 7 to 0, and then we can just fill it 4 bits at a time and shift it left until we have the entire thing. So going from up top to bottom. So if this is we are reading int 0, then we just need to return this dot the result or equals pin dot RQ value, just or we call it status, just the row status. And if we are reading, and eventually we are going to return this result. So if we are reading the enable, so that would return IRQ enable mask proc 0, and eventually we'll have a different enable mask per processor. And proc 1, proc 0 force, so it will return IRQ force mask. And then if we want to have the interrupt status, it's just pin.irq status and pin.irq enable bitwise or with IRQ force mask. The same logic that we had for alarms. Okay, great. I think we have interrupts. I'm not sure. I've written too much code, so I'm not sure if I missed something. So if I did and you happen to be still following, let me know in the chat. Otherwise, I think that other than testing it, which will probably reveal that there are many bugs, we have completed writing, implementing GPIO. Yeah, so I think the thing I would really love to do is to write tests for all of this, but it will probably take a lot of time to test everything. And I have this priority to get the PIO to programmable IO for the course. So I think we'll do PIO in the next session. But yeah, let's maybe start doing the tests, and then I will probably continue them in an offline or maybe a spontaneous session. Yeah, before we go into the test, let's just run this once more, like one more time. We see that Blink is working, and there is also like where is the SDK examples? Yeah, there is also. Thank you, Steve. It's done, but it's without a test, so I'm not sure I would call this done. But yeah, there is like GPIO IRQ. There is like a test program for the GPIO IRQ. So let's try to run it and see if we happen to be lucky. Probably not. There must be some bug here. I would be surprised if this runs smoothly. So build GPIO low GPIO IRQ. Load GPIO IRQ.hex, copy it to RP2040 JS, and let's try to run it. And right now it shouldn't do a lot of things because we still don't, our test code still doesn't generate the IRQ, but we'll add it in a moment. Let's have this run hello GPIO IRQ npm start, and let's see. Yeah, it prints hello GPIO IRQ. Interesting. And implement peripheral to this address. This address should have been implemented, so I guess we are missing some return. Where is that? Yeah, we should probably return here after writing, so we don't get into this switch case, which we don't actually need. We don't actually use this switch case. We can probably just call super in this case without the switch. Okay, so now we shouldn't be getting those unimplemented, and we can already see that there is like some writes that are going to those RQ registers. And what I'm going to do now, I'm going to just emulator run. So let's see what the low RQ does. It listens on which pins? GPIO callback. Yeah, probably GPIO number 2, right? Yeah, there is no docs for that, but I guess this is the GPIO number, and these are like the events, rising edge and falling edge. So yeah, I know I keep switching desktops. So we need to basically we can do something like that. Just generate those events artificially, changing GPIO2 value to let GPIO2 value is false, GPIO2 value, and then can actually change it. And then we can call mcu.gpio2.set input value to GPIO2 value. Yeah, I guess. Oh, and let's do it after 300 milliseconds. Just yeah, I think I'm using it here. Why does it say it's never reassigned? Oh. Good catch, Yeslin, thank you. Yeah, let's run it and see if it changes. Yeah, changing GPIO2 value to true, so it did change the value to true, but we didn't get any kind of IRQ, I guess. Yeah, so it doesn't work first try. Let's try to quickly debug it. So console log update IO interrupt, just to see if we are getting there. And yeah, we can probably lower the timeout, and yeah, we are calling update IO interrupt. And let's see also what's the RQ value here. So the IRQ value is true. It has an interrupt request, so maybe there is a bug here. Console log set interrupt IRQ bank 0 and interrupt value. And let's see what's going on here. Yeah, so it sets the interrupt to true. So I wonder why we don't get the interrupt handler running next. That's strange. Let's try to attach GDB. So maybe that would give us some clue to what's going on. So GDB multi-arc target remote winhost 333 and file load GPIO IRQ.health Yes, whatever. Or maybe not. Yeah, I'm not in the right folder. Let's just run it in its own terminal. Okay, where am I? GDB connected. Don't have debugging symbol. Yeah, it's probably just in a busy wait, just calling itself. But then I wonder what happens with this interrupt. Why it doesn't fire? Let's see inside set interrupt what's going on. So probably console log interrupt is pending. IRQ. Change this to run after 1 second so we don't have to wait so long. Yeah, it sets the interrupt to pending, and then inside interrupts updated. Interrupts updated. Check for interrupt so we can see if we are finding this interrupt. Console.log exception entry to interrupt and interrupt number, just to see if we are actually getting into the interrupt handler. No, so something is wrong here. It's probably yeah, console log, check for interrupts, and let's see, interrupt set this dot enabled. Maybe it's not enabled. Maybe we are firing the wrong IRQ number. Yeah, we can see it checks for interrupt, but interrupt set is, yeah, let's see, is 0. So, and we have some interrupts that are enabled. Let's print it as hexa so it will be easier to see which bits are set. But I think, yeah, we are firing the wrong interrupt, I would say. I guess it makes more sense that we are firing the wrong interrupt rather than this is probably the interrupt it's listening for. I'm wondering what did we get wrong, but it's pretty encouraging that it fires the interrupt. We just probably got the yeah. So yeah, enable dormant wake isn't interesting, or the 6 GPIO. Okay, but it doesn't say the interrupt number. And here we have IORQ bank 0 is 19. So did I miss anything? Let's try to figure out from the SDK code. So it's calling not that one. Hello GPIO. It's calling set GPIO enabled. Let's go to the SDK and look at the source code of this. Leave me alone. All right, so there is probably something that attaches to the interrupt. IRQ handler. Where does this attach? IORQ bank 0, 13. Interesting. This one said 13, and this one, oh, yeah, I should have looked at this column and not this one. Yeah, my bad. So first bug found. Hooray! Yeah, let's go back here and remove this console log because we are optimisting. Console log, and then just fix the interrupt number. It should be 13. Yeah, okay. So now let's see if we get it to work. That's interesting. So first of all, we get GPIO 0 edge rise. I wonder why it says 0, but 0, 0. Why it says 0, but it did run the handler. And there is probably a bug here when we try to read from the interrupt status. I wonder why we get undefined here. So pin should go. Oh, I think I know what's the reason. So I guess, yeah, I guess we just have some empty slots in this register. So if we take a look at the registers, probably the last one in each group, yeah, it has like those bits empty. So basically, if this is, we can fix it by saying if not pin, then continue. So we just ignore this, and same for writing. So if we don't have such a pin, it's out of range, just continue. And let's see if this fixes the issue. Yeah, so it seems like the interrupt triggers, but it doesn't clear. And another issue is that it says like GPIO 0, and let's take a look at the code and see why it says 0. It feels strange that it says 0. That was in the Pico examples. And then we have the code here, GPIO callback, get the GPIO number. Yeah, so these are like two bugs that are probably related in some strange way. So I guess we are probably not updating the right thing or something like that. Let's console log offset to string 16 and start index just to see if we got it right. And then yeah, value to string 16. Let's see all the writes that happen and see if we can figure this out. Yeah, so it always like writes to F0. What is that? So that's 0. It writes the value 8. So I think it tries to so writing the value 8 to this address is basically trying to clear GPIO 0 edge high. So it's probably getting the wrong GPIO number and it's trying to clear the wrong one. So the problem is not here. It's probably with reading, and I think I know what the problem is. We said that we would just take this result and each time we will shift it left by 4 bits after we update it, but we haven't shifted it. So let's do it. So that should probably also be fix the issue with this GPIO being 0, or maybe not. Okay, it's almost, now it's 3. So I think we are shifting it one time too much. We shouldn't shift it for the last one. So if index, or maybe we can just shift it before we update the value. That should also do the trick, probably. Yep. Yes, you can see it works. So we have here a low GPIO IRQ and then GPIO 2 edge rise, because that was we set it to true. And just to further check it, so let's also change it now. GPIO value, let's do another timer with the same logic, so it will just toggle it after 3 seconds. So we expect it to go high and then go low. So yeah, rise and then edge fall. Perfect. So Yeah, this doesn't prove that the implementation is perfect, but it proves that at least the basic test program works, and we found a few bugs. Yeah, oh, we don't need this. Just wanted to remove this. Where is that coming from? Maybe I just forgot to save after removing that console log. Yeah, I think. Yeah, perfect. So, thanks, Gunther. I haven't seen you before, so nice to see you here. I hope I pronounced your name correctly. Anyway, so we are in a kind of interesting state here. Yeah, this is like the first bug fix. Then this is like the second and third bug fixes. Yeah, so we are in a weird state here where we have like this sort of working GPIO implementation. I'm not sure if it's complete. It probably has some bugs, and we still haven't tested it, but we know it works for at least this basic case of this low GPIO IRQ, which is quite nice. So I'm going to commit it for now. Fit GPIO basic working GPIO implementation, and we also have an issue number, right? I knew we had one, so that would be 20. It's still not tested, unit tested, but at least hello GPIO IRQ runs successfully. Maybe we can include here where was this? Yeah, this code just to let's improve it a bit before including it in the commit. So instead of UART send, let's do it sys process.std_out write value new int8 array. And so I'm just preparing a quick sample for the commit, so I'm just making it super simple. So if anyone wants to run it, and instead of set timeout, let's change this to set interval, so we don't need to repeat it. So if anyone wants to try it at home, they can just paste this example from the commit, and now yeah, we can see like the output even more it's easier to see like the output without all those UART prints. Cool. We can just paste this a copy of this test code into the commit message in case someone wants to try it at home. Yeah, and yeah, let's also say that this closes 20, and we'll have I will open another issue later to remind us that we need to add the tests, or at least some tests, but at least now we have this implementation 2 weeks later after we open this issue. And I think that would be a good opportunity to, just release a new version with all the fixes from Valerio, the integer divider, the spinlocks, and now the GPIO. And finally, we are starting to get into a place where this emulator is starting to get useful. It can already sort of run MicroPython, and it can already let's just do it in a clear terminal. So yeah, terminal, so I don't run into issues with the environment variables for the tests. Anyway, so we can run MicroPython, at least get to the beginning of the interpreter, and probably further once we have UART input. Maybe we'll have another stream for that. And we have GPIO and timers that are mostly working. And my plan for the next session would be to start working on either the PIO or multi-core emulation. Still not sure where this would go. Let's see. Yeah, we added a bunch of new files, and we can release a new minor version with those new features. Great seeing everybody, and thank you for joining the stream today. It was a lot of code, I think more than the usual, just writing code for a long time. I hope it was still interesting. And yeah, I'm happy that we managed to at least complete the GPIO feature. And I want to wish you a great rest of your week, and see you again on next Tuesday. So bye bye to you.